All right. Chapter 3, as you recall, was about polynomial functions. They could have been quadratics, they could have been x to the 5th power, the 7th power, whatever. But it was about those types of functions and equations. Chapter 4 is dealing with several different types. The first of which here is exponential functions. That means either we're raising x to a power or we're raising some base to some form of x. X could be in the exponent or it could be in the base. So, with that in mind, here's a quick review. Let me back up just a minute. All right, if I start with something like this, I'm color coding it. If I start with this, I've got a fractional exponent here. And this is saying, if you raise a to this fractional exponent, what does that mean? It means one of two things, both of which are equivalent. First of all, you could say, go ahead and raise a to the m power. The top number there is the power. Go ahead and raise a to that m power, and then take the nth root of it. So you could visualize it as raise it to the power first, then take the root indicated. That's one way to visualize it. Another way would be, no, take the nth root and then raise that result to the m power. These two things right here are equal. And sometimes you'll want to visualize a problem the first way, where you're raising it to the power first and then taking the root. Sometimes the second way, where you're taking the root and then raising the result to a power, will help you solve the problem easier. So just realize those last two things are the same out there. All right, so here's an example. I'm trying to keep the color coding the same. So 4 to the 3/2 power. So the bottom number is the root, the top number is the power. I could visualize that this way. Raise 4 to the 3rd power, then take the square root.
Mr. Walden, I'm supposed to go help with the NHS stuff.
Okay.
Sorry.
Well, don't be. It's a neat program, I imagine. So I'm going to raise 4 to the 3rd power. So when I raise 4 to the 3rd power, that's 4 times 4 times 4. So that equals 64. So I'm taking the square root of 64. I know normally we don't put the little 2 up there for square root, but it's understood to be there. But this is just to illustrate how this all plays out. Well, which is 8. That's one way to visualize 4 to the 3/2 power. The other way is to say, I'm going to take the root first, like this. So this says take the square root of 4, and whatever you get, cube it. So the square root of 4 is 2. And then 2 cubed, 2 times 2 times 2 is 8. So I should get the same answer either way I do it. I'm just saying sometimes one approach is more difficult than the other when you start working problems. And another thing, notice these came out even. And most of the ones you're going to work with will. come out even. But instead of having 4 as the base, what if I had 1.3? Then it's calculator time. You'd solve it the same way, and then just however many decimal places the problem will ask you to round off to. But these rules apply even when it doesn't come out even like 8 here. All right, let's try this one. 36 to the negative 1/2 power. What's that negative do? What does that force us to do?
Put a 1 over it.
Exactly. Put a 1 over it. Like that. Thank you, sir. Now, I know anything to the 1/2 power is the same as the square root. Looked at it another way, you could say, well, I'm raising 36 to the 1 power. Okay, that's 36. Then I'm taking the square root of it, which is that. And so then the square root of 36 is 6, so there would be my answer. And some of these you're going to look at and go, I don't see how that, works out. Some of these are not intuitive at all. Some of them are. Like example 1, not bad. Example 2, you start getting a little sketchier because it's to the negative something. But just remember, you just stick a 1 over it. Okay. So I'll get this back. All this is saying is, if you've got some base, I'm just calling it K. If you've got some base, I'm raising it to a power like A. And then whatever I get for that answer, I'm raising that to another power called B. That a shortcut says to just multiply those two exponents. All right, so for instance, x to the 3rd power, and then you raise that to the 4th power, is just x to the 12th. And then here's one with a negative 1/2 power. Same rule applies. I just multiply the negative 1/2 times 6, which gives me that. Which gives me that. Which gives me that. All right, so x to the negative 1/2 power, whatever that comes out to be, then we're raising the result to the 6th power is just equivalent to x to the negative 3 power. Maybe not so intuitive on that one. Let's add that one last little thing there so we don't have a negative exponent. So realize that these two things right here are the same. All right, so let's take a look at another rule. And this rule says if you've got the same base, K in this case, if you've got the same base and you've got it raised to exponents, the only way that can be true, the only way those two things can be equal is if A and B are equal. So same base, raised to these powers, you know that A has to equal B. Now this has another twist to it. Right here, it's saying if and only if Anybody remember what that means? Sounds so legal. It means it works both ways. See, in the first instance, I'm saying, well, if this is true, then this is true. But I could say, if this is true, then this is true. It goes both ways. Some things don't go both ways. If I said, if I have a dog, it has 4 legs. That's true. I can't turn that around and say, if I have an animal with 4 legs, it's a dog. That may or may not be true. So this works both ways. Works both ways. All right. Let me do this. I'm going to erase a little bit of stuff here. Nah, I'm going to leave that. Well, that just jimmied everything up, didn't it? So I've got 2 to the x plus 1 power equals 2 to the 2x minus 3. I wrote over what I already had. Now look at it. My bases are the same. So what do I know? I know that this exponent equals this exponent. So I know x plus 1 has to equal 2x minus 3 because that rule up there at the top. So I can subtract x from both sides, and I get 1 equals x minus 3. And I get x equals 4. Now, some of these without that rule at the top would be pretty tough to solve. It'd be a guess and check thing. So let's check it. So is 2 to the 4 plus 1 power equal to 2 to the 2 times 4 minus 3 power. I'm just going back to this original thing here. 2 to the 5th, 2 to the 8 minus 3. Yeah. So my answer was good. It doesn't hurt to just take a second and check these, especially on a test. All right, let's take a look at another one. Well, I'm jimmying this thing up. I'm pointing out that the base is the same. The base is the same there. If you're somebody watching this video, I apologize. Let's take a look at another one. See if I can get this one better. This one's different. Is the base the same here? Apparently not. I'm seeing a base of 1/2 on the left-hand side and a base of 8 on the right-hand side. If I visualize a little 1 being right here.
You can just make 8 equal 1/2 and then to the exponent.
Could. So 8 is equal to 1/2 raised to what power then? That might be kind of tricky. You could visualize it like that. And the deal here is the bases are not the same, so try and make them the same. Now, if you want to try the approach of making 8 some power of 1/2, and you can make it work, that's great. I'm looking at that 1/2 on the left-hand side. Is 1/2 a power of 2? Anybody? In other words, 2 to what power gives me 1/2? 2 to the 1/4 power would be the 4th root of 2. See, to get that 2 to go from there to the denominator, it's going to have to be a negative power. So 2 to the -1? Because what's the rule? You just stick a 1 over the whole thing and remove the negative sign. All right, so on the if you agree with me on that, on this side I've got 2 to the -1 power raised to the x power. My base is 2. Is 8 a power of 2? Yeah. So now my bases are the same. I'm not saying you couldn't use the approach where you make 8 some power of 1/2. You could, but I think that's going to be harder to see, just in my opinion. All right, so now then I'm going to do what? I'm going to multiply these two exponents together. And I get 2 to the -x power equals 2 to the 3rd power. I can just look at that and go, well, -x equals 3. How come? Because this rule right here, before I did all this junk. So I know that what, x equals -3. How would I check that? I'd go back to my original thing and I would have 1/2 to the -3 power. Does that equal 8? All right, 1/2 to the -3 power, that's a negative power. So I put a 1 and then my 1/2 and make that a positive power. Does that equal 8? Well, I've got 1 over, what's 1/2 times 1/2 times 1/2? So now I'm going to keep change flip. So I've got 1 over 1 equals, I'm going to flip my divisor here. So, yeah, same. So it just takes a second to check them because some of these can get weird. Is this anything like what we've already seen? Is there a pattern here? Yes, there is. So I'm seeing a 3 over here on this side. I'm seeing a 9 here. Is there any relationship between those two numbers? Yeah. So I'm seeing a 3 and a 9. That 9 is related to the 3 because it's 3 squared. So I could rewrite this as 3 to the x plus 1 equals 3 squared to the x minus 3, couldn't I? Have I changed anything? Just the form. So now my bases are the same. So I could say 3 times x plus 1. Now I've got to multiply this 2 right here times all of that. So it's 2 times x minus 3. Don't forget you got to distribute that 2 across that whole exponent on the outside. Where are you going to mess up? You're going to say 2x and then just leave the minus 3. So don't do that. So I know now that x plus 1 equals 2 times x minus 6. I subtract x from both sides, I get 1 equals x minus 6. So x equals 7. A quick check. Does 3 to the 7 plus 1, that's the 8th power, right? Now over here I could say 9 to the 4th power and get a calculator out and figure it out. Or I could say, well, this is really 3 squared to the 7 minus 3 to the 4th power. 3 to the 8th equals 3 to the 8th. Yeah, we're good. So it just takes a second to check them. All right, let's take a look at another one. Now notice on both that one, even this one that I scribbled out, we've had a base of some number, and then our variable was part of the exponent. Not so in this case. This is a different flavor of exponential equations. Now what do I do? Well, now remember, we can visualize this as either x squared and then take the cube root of it, or the cube root of x and then square it. I can visualize that either way. For this problem, I think this way might be the best way to visualize it, because on the left that would give me, and that should be a cube right here, cube root. This would give me the cube root of x squared. Can I visualize that right-hand side as something squared? 5. Now what can I do? Remember that square root property from way back when? It said if you got something like this, you can just take the square root of both sides. So if I take the square root of both sides, I've got the cube root of x equals plus or minus 5, don't I? Okay, now what? If I've got the cube root of x on the left-hand side, what can I do to both sides now to undo the cube root? Okay, thanks, I can cube it. That means I've got to cube this. So over here on the left-hand side, I've just got x, which is what I wanted. Over here, I've got either negative 5 times negative 5 times negative 5, which is negative 125, or 5 times 5 times 5. I'm getting that. How would I check that? Let's check the negative one first. So, negative 125 to the 2/3 power. It says either I could square negative 125 first and then take the cube root of that, which would be what? That kind of thing. That's going to take a calculator for me. 125 times 125, and then take the cube root of that. Or I could take the cube root first. I could say negative 125, the cube root of that, and then square it. Well, the cube root of negative 125 is negative 5. Squared is 25. And that's what I got up here. Now see, that worked because I can take the cube root of a negative number. I can't take the square root of a negative number. But I can take the cube root of it. And I think you'll find if you check the 125, it's going to work out too. All right, how about this one? This one's like the first kind of problems. We've got x as part of the exponents here. I'm seeing a 2 here and a 4 here. Any relationship? Yeah. 4 is the same as 2 squared to the x minus 2 power. Oh, now my bases are the same. So I can say two to the, I've got to multiply this 2 times all of that. So that's going to be 2x minus 4 equals 2 to the 3x plus 3. So I know 2x minus 4 equals 3x plus 3. I subtract 2x from both sides. I'm getting x equals negative 7. Not that intuitive on this one. But it would check out, and just because we got a reduced time today, I want to get to the last example. But I think if you check that, you'll find that it works. We might come back and check it if we have time, but let's look at the last example here. Holy cow. This is one of those second kinds of equations where x is the base. What do I do here? Well, I can visualize this as just 1 over x to the 6th, right? If we're good with that, can I cross multiply? Just a proportion now. So I'm cross multiplying, so I've got 1 times 64 is 64. Equals x to the 6th. Now what? I can take the 6th root of both sides. On the right-hand side, I've just got x. What times itself 6 times gives you 64? All right, thank you. And again, I think you'll find that that checks out. That's what section 4.2 is about. Now,